Welcome, this is Daniel Morden alongside Braden Haldezos and Brendan Omoto presenting to you our take on Project 1, Motion of a Helicopter. In this situation, we have a helicopter, one to be used for the next Mars rover. From rest at t equals negative big T, the helicopter launches and flies for a duration of time before landing at a known horizontal distance away. Given the situation and equation for acceleration of time, we must describe the helicopter's motion, its time in the air, and where it lands. Based on the information, we have three constants, beta, alpha, and big T. We can tell that beta is a constant for the x component of acceleration, as it is being multiplied with x hat, the horizontal unit vector, while alpha is multiplied with y hat, the vertical unit vector. Since big T is a constant time value, we will consider it as an interval of time that indicates the motion of the helicopter we need to focus on, which can be manipulated depending on our needs.
So we're going to take a look at the graph of the x component of position for the helicopter. Beta has been chosen as a reasonable value, as you can see it's 5, and the path of the helicopter is from negative big T to T. We have set big T equal to 2, so the domain of this graph from negative 2 to positive 2 is the motion that we will be paying attention to. You'll see that there is a initial increase in position, kind of a slow increase in the horizontal direction, but as we get closer to the origin, as we get closer to 0, and as we go past 0, you'll see that there is a faster increase in horizontal position, and then as we get closer to 2, you'll see that the increase in position kind of slows down. We can move on now to the graph of the y component of position, and you'll see something similar. So once again, big T is equal to 2. We've picked a reasonable value of 5 for alpha, and you'll see that there is a small increase in vertical position of the helicopter from about the interval of negative 2 to negative 1. This corresponds to the helicopter moving up as a helicopter normally would, and it's traveling in some horizontal direction during the interval about negative 1 to positive 1, so we don't see any vertical change here. This is represented by the graph. And then from the interval of about 1 to 2, we see another increase in vertical direction, indicating that the helicopter is once again moving up the same amount of distance that it did from the ground to whatever position it is at from the interval negative 2 to negative 1. So now we can move on to what the path of the helicopter probably looks like. We've analyzed both of the position graphs, and combining them, we can get this sort of motion where we have a small increase in the x direction, then a larger increase in the x direction, and then once again a smaller increase in the x direction. This corresponds to our first graph. And if you look at the vertical position, we have a rather large increase in the vertical direction of position, and then there's no increase. It's flat, while the horizontal distance is increasing a lot. And then you'll see towards the end, the helicopter goes up the same amount of distance it did in the beginning, which corresponds to the second graph. You'll also notice that the interval of time that it is from negative big T to T is what Paul characterized as little d in his explanation video. Moving on to the velocity in the x direction, I've included the position graph, but I've made it kind of easier for the eyes to see by changing the variables beta and big T. So this time we're going to be looking over the interval negative 8 to positive 8, because big T is equal to 8. The velocity graph is that blue graph, and you'll see that as the helicopter initially starts to move forward, their velocity is rather low, and as it gets faster and faster, the velocity gets higher and higher, and when we're at the origin, the peak velocity is reached. As the position starts to increase at a slower and slower rate, with the red graph, you'll see that in correspondence, the velocity is still positive, but it's decreasing. So there's no negative velocity. The velocity is still positive, but it's just decreasing, which correlates to the helicopter moving in the positive x direction at a slower and slower rate. And you'll see the starting and ending velocities, the final and initial velocities, are both 0. If we look at the y component of velocity, we'll see something kind of similar. So I've graphed the position graph here just so you can get a better reference. We've taken it and shaped it so that you can see it on your eyes. Big T is equal to 4, alpha is equal to 10. So we're going to pay attention to the interval of negative 4 to 4. You see an initial spike in velocity when the helicopter initially moves in the upward direction, and as it gets closer and closer to that flat position path that we kind of looked at earlier, you'll see that the velocity kind of goes down from about -3 to -1 because the helicopter is no longer changing direction in the y direction during this time. And as the helicopter approaches its second interval of increased position, you'll see the velocity starts to go back up again to account for this. And as the helicopter reaches its final position and it comes to rest, the velocity drops off again in correspondence with the path of the helicopter in the y direction. Now we're going to look at the acceleration in the x direction of the helicopter. Big T is equal to 3, so we're going to be analyzing -3 to +3. I know it's a little bit cut off, but we have reasonable values for beta and alpha. So the acceleration is positive from the interval of -big T to 0, and the acceleration is positive, but it is decreasing. So we're still going to have positive acceleration until 0, but the acceleration of the helicopter in the x direction is just going to be at smaller and smaller intervals. Then, when big T equals 0 is reached, we have a change in direction of acceleration, right? Because the acceleration goes from being positive to negative. And what this means is that the helicopter is accelerating in the opposite direction. We have a still decreasing acceleration, and this accounts, if we can go back to the graph of velocity in the x direction, you'll see that the velocity here is decreasing after big T equals 0 to big T equals 8, or I guess in this case for acceleration, big T equals 3, but it would be the same. So that negative acceleration is what is accounting for the decrease in velocity for the x value of the graph. Now let's take a look at the acceleration of the helicopter in the vertical direction. We know that the position of the helicopter initially increases, then it flatlines for a while the helicopter travels in the x direction, and then the helicopter increases once again in the positive y direction. So this corresponds directly to acceleration. If you take a look, the acceleration is initially positive, but it is decreasing. This corresponds to the helicopter accelerating in the y direction, and the helicopter reaches a certain point. It looks to be at about when big T equals -2.4, when the acceleration becomes negative, or the helicopter starts to decelerate in the y direction, and it'll come to a 0 value of position. So if you looked back at the position graph, you would see this. This corresponds to the helicopter accelerating in the y direction and then kind of neutralizing and going flat. And it's going flat for a while, and once it reaches its second peak of position, when it goes back up again, you'll see that the acceleration increases, and as the helicopter once again approaches rest, you'll see that we have negative acceleration at around the 2.4 mark, resulting in a change from positive acceleration to deceleration, or acceleration in the negative direction, to allow the helicopter to come to rest at big T equals 3.
A part of sense making is having the units equally balanced and physically correct. For example, for their horizontal and vertical positions, we should come out with units of length, in this case meters, and for big T, the unit should be of time, in this case seconds.
When we increase or decrease our values of alpha, beta, and big T, we can start to see correlations when we have higher and lower values, as well as the positions of alpha, beta, and big T in the numerator or denominator. With big T being at the top of both the delta x and delta y equations requires higher displacement in both the x and y directions. Beta being in the denominator of both the big T and delta y equation shows that the smaller the beta value, the higher the big T value, which in turn also gives us a higher displacement in y. At a given time in the air, a smaller big T value would yield a higher instance of acceleration. Assuming our helicopter lands at a higher y position than its initial, does our answer make sense? Yes, the path of the helicopter follows that of a real helicopter. When visualizing the problem, we expected for our helicopter to begin its course at time -big T and land at big T. Our x acceleration is decelerating towards our final distance, and our velocity graphs model the helicopter's gradual inclines, at times traveling at a relatively constant speed, as well as the inclines and declines towards our helicopter's eventual landing. In the problem, there are no specifications or parameters that our helicopter's starting and landing elevations are the same. As we've done in our example graphs, we've plugged in test values, and we can see that our graph shape and characteristics hold. Therefore, we can make physical sense that our scenario is realistic. Similarities and differences. Problems such as the Mario problem we did in class, or the stoplight problem in homework 2, involving identifying the constant in big T, which in the Mario problem meant the duration of the star power-up, and in the traffic light problem, the time the light goes from green to red. For our helicopter, big T meant the interval of time spent in the air. For all of these problems, we were given acceleration or velocity functions, and we can use those to then integrate for the function of position. Arithmetically speaking, this is done the same way for each of these problems. The idea of taking into account separate x and y components for a helicopter problem is that of like our Homework 3 cliff problem and the marble problem in class. There was no use of the trajectory angle, like with the marble and cliff, but these problems are fundamentally the same in the initial setup of a 2D motion problem, as well as combining x and y components if needed to rearrange and solve for specific symbolic equations. A couple of differences come from the perspective that with all of our similarities, integrating, identifying constants, 2D motion and sense making, this is the first time we've had a problem where everything we've learned so far is utilized, which has never been done to this degree. With our job being to sense make and perform analysis, this is the most intricate and in-depth we've looked into what defines our helicopter's motion in every aspect. This has been our helicopter motion problem. Thank you for your time and the opportunity, and have a wonderful rest of your day.